Hello friends, my name is Jimit and welcome back to the Civil Technology channel. So in this video, we can discuss about how we can design the doubly reinforced rectangular beam section. In previous tutorial, we seen how we can design a singly reinforced rectangular beam as per the IS 456 codal provision. But that types of problems is very rare in real-time building, real-time structural model. So that is just for understanding purpose. Procedure is very much important in that example, so that we can use for further more complicated beam sections design. So from today onwards, we see a little bit complicated, little bit different types of problem that very much near to the real problems, real building beams. Okay, so let's start it. So here also I am taking one example, and using that we can understand how we can design the doubly reinforced beam. Okay, few procedure is very much same like a singly reinforced beam, but some other parameters and some formulas and some other things will be different in every type of problem. So please note it. And if you didn't see the first video, that is singly reinforced beam section design, please watch it. I will give a link in a description. Also you can get from above the I button. So problem is a rectangular beam whose dimension is already given 230 by 600 mm. Effective span also given, that is 6 meter. Okay, so here I am directly taking the effective span for reducing the time for the calculation. You can see in previous video how we can calculate the effective span and effective depth of the beam section. Effective cover for reinforcement given as a 50 mm, both from the tension side also and compression side also. Imposed load, that is the live load, is given 40 kN per meter, and grade of concrete and grade of steel here given M20 and LP 415 respectively. So let's first list out the given data and note down please on your copy, so further calculation you can easily correlate the input data. So these are the notations that we use for a particular type of given data in our further calculation and formulas. If you see in diagrammatically, then it's look like this. This is our longitudinal section of the beam. This is beam. These both are the supports that may be column or wall depending upon the problem. Effective span means center to center distance of these two supporting walls or columns that directly given in a problem, 6 meter. And if you look like cross section, then it look like this. This is the beam 230 mm, overall depth given as 600 mm, and these both are the cover, effective cover, that given as a 50 mm. So let's start the solution. So first we have to find out what is the effective depth. So formula for effective depth is overall depth minus of the cover from the tension side. So as we seen, from tension and compression side cover is 50 mm, so just directly we deduct from our overall depth, so we can get the effective depth 550 mm. So this depth we use for our moment and shear force calculation. So please note down this effective depth value somewhere. Also I will give that value here also, whatever we calculate, so you easily correlate the things. Next step, we have to design in a moment. Okay, so as this is a rectangular beam and we all know the maximum bending moment from simply supported rectangular beam is WL square by 8. If your beam is something like else, like cantilever beam or continuous type, then your moment formula will be vary depending on the beam type of the beam. So for that, first of all, we require the load. What are the different types of load coming on the beam? Based upon that, we can calculate the moment. So first load is the sulfate, that is the sulfate of our beam. So its formula is B into D multiplied by gamma, that is the density, and we find out the UDL. So we can take a length as a 1. Per meter length, we have to find out the loads. So all the values already given in the problems. Just here you can see width of the beam 230 mm, overall depth 600 mm, density of the concrete 25 kN per meter cube. So simply just put down the values and you can get the sulfate of beam 3.45 kN per meter. Impulse load, that is the live load already given in the problem, that is 40 kN per meter. Okay. So directly we can calculate the design load, that is 1.5 times dead load plus live load. So this 1.5 factor will vary depending on the different load combination that you can get from the IS code, respective IS codes. But for a conservative side, I am taking the maximum factor, that is 1.5. So just put down the dead load and live load value, so you can get the design load for our moment calculation, that is 65.175 kN per meter. So this much load, for this much load we have to design our beam, and accordingly we can decide the reinforcement required for our beam. So let's calculate the moment, as this is a simply supported rectangular beam. So design moment formula will be WL square by 8, where WU is the design load, means factor load. So keep remember the load here we taken as the factor load, and length also we have to take an effective span, not the clear span. So just put down the value, you can get the design moment 293.29 kN meter. So this much moment comes from all the loads which carry by this beam. Similarly, we can find the design shear force for our beam, and as we know, for rectangular simply supported beam section, design shear force is WL by 2. So simply we can get the design shear value 195.525 kN. So these are the two major values. Based upon that, we can decide what are the top and bottom reinforcement for our beam and what are the shear reinforcement, that is the stirrups coming out from our beam. So please note down these two values, which is very much important. Next step, we have to check whether our section is singly reinforced or doubly reinforced. So if you see in the last video, you will understand how we can get whether our beam is singly reinforced or doubly reinforced. So for that, we have to calculate one factor which is called as the axial limit. So for axial limit, there is a formula for different types of steel. Like for Fe415, its formula is 0.48 times the effective depth. If your steel grade is something different, then your axial limit will be calculated from different types of factors, and just multiply that factor with the effective depth of your beam. So you will get the axial limit. So in our case, axial limit will be 0.48 times 3, that is 0.48 times 550. So axial limit value coming out is 264 mm. Using this axial limit value, we can find out the ML limit value, means what are the maximum moment this beam will be carried safely as a balanced section. So let's find out. So formula is 0.36 multiplied by FCK, that is the grade of the concrete, multiplied by B, that is the width of the beam, multiplied by axial limit, multiplied by D minus 0.42 times axial limit. So just put down all the values. We already have all the values here, you can see. So if we put down all the values, we can get the MU limit value, and that is the 191.98 multiplied by 10⁶ Newton mm. As we calculate all the moment and shear force value in a kilonewton meter units, so we have to convert this moment in a kilonewton meter unit. So it coming out 191.98 kilonewton meter. So this much moment this beam carries safely as a balance section. But as you seen, our MU design moment, that is MU, which is higher than this MU limit value. So it means we cannot design our section as a singly reinforced section. So we have to provide some extra reinforcement to balance this both the moments and make our section as a balanced section. So how we calculate that, that is the different thing, that is the different part of this example that you never seen in a last example. So that part is very much important here. So let's start how we can do that reinforcement calculation. Okay, so simply just MU limit is very much less than the MU value, so we have to design our section as a doubly reinforced section. So here two types of reinforcement coming. First is the tension reinforcement and second is the compression reinforcement. Tension reinforcement for simply supported beam, tension reinforcement coming out at the bottom of the beam. So whatever the steel we have to provide at the bottom, that we call as a tension reinforcement. So how we calculate? So if you read the IS 456 carefully, you can understand. For that we have to equate the compression force, that will be equal to tension force. So whatever the compression force coming out and whatever the tension force coming out, just we have to equate both the things and we can get the AST1 value. So here is the formula: 0.36 times FCK multiplied by B into actual limit. That is our compression force which act on the beam, and tension force is the 0.87 times Fy into AST1. See here all the values we already known except AST1. So just put down all the values. That is 0.36 times 20 multiplied by width is 230, actual limit 264, 0.87 times Fy is 415. So you will get the AST1 value, and that is the 1210.9 mm square. So this much reinforcement actually required if our section was singly reinforced section or for a balanced condition. But as our section is doubly reinforced section, we require to provide some additional reinforcement to make our section as a balanced section. So that additional reinforcement we can find out whatever the extra moment that we get from the differences of MU limit and MU. So just find out the MU2, that is the additional moment. For that we have to calculate the additional reinforcement. So just this formula is simple: MU, that is whatever our design moment, minus of MU limit. We have both the values, just put down. So you will get the MU2 moment, that is the 101.31 kilonewton meter. So for this much moment we have to calculate additional reinforcement. So formula is 0.87 times Fy into AST2 multiplied by D minus D dash. So here D dash is the effective cover. If you remember the diagram that we see in at the start of this video, so you can correlate easily D dash is what. So MU2 we already have 101.31, just convert into the Newton mm, because all other values we put down here in a Newton mm. Newton mm factor. Yeah. So 101.31 multiplied by 10 raised to 6, that will be equal to 0.87 times 415 into AST2 multiplied by effective depth 550 minus of effective cover 50. So you will get the AST2 value, that is 561.2 mm square. So this much additional reinforcement we require to make our section as a balanced section from tension reinforcement side. So here the total tension reinforcement coming out is AST1 plus AST2. Okay, so simply we have to add these two values and we can get the AST required value, that is 1772.1 mm square. So this much reinforcement we require at a tension side. So for that we have to select the dia. I select the 20 mm dia. So we require the 6 bars of 20 mm dia to resist this much moments and counter this much reinforcement. So AST provided is 6 times pi by 4 multiplied by 20 square, that is 1884 mm square, which is greater than AST required, so it is okay. Likewise, we calculate the tension reinforcement for our doubly reinforced beam section. Next step is to calculate the compression reinforcement. As we seen, there are two types of reinforcement, tension and compression. So for compression part we have to see at what strain our beam section will fail, or at what strain our concrete will fail. Based upon that strain, we have to calculate the yield strength of our steel at that strain point, and using that value we can calculate the reinforcement. Okay, this is the normal concept behind the compression reinforcement. Let's see in a procedure wise so you can understand more better way. So here is the formula for compression strain, that will be equal to 0.0035 multiplied by XU limit minus D dash, that is effective cover, divided by XU limit. So just put down all the values, you will get the compression strain value, and that is 2.837 multiplied by 10 raised to minus 3. So for this strain we have to calculate the yield strain of our steel. So for that we have to refer one graph that is given in the IS456. So if you refer the IS456, you will get this graph from stress versus strain diagram. So here somewhere you have to see where the 2.837 multiplied by 10 raised to minus 3 value coming, and based upon that you have to select here the stress. So if you see carefully, then you will get the compression stress value is 0.845 times Fy. So this is our compression stress, and based upon that we have to calculate our area of reinforcement. So just put down the Fy value, that is 415. So compression stress value will be 350.7 megapascal, that is Newton per mm square. So here is a formula, FSC multiplied by ASC, where ASC is the area of compression reinforcement, that will be equal to 0.87 times Fy into AST2. So just put down all the values, you will get the ASC value. We already calculated the AST2 in tension reinforcement step, so we will get easily. Fy value we know, FSC we already calculated here. So AC you will get the 577.76 mm square. So this much reinforcement, this much steel you have to require at the compression side. So here I select the dia of bar is 16 mm. So for that we require 3 numbers of the 16 mm dia bar, and our ASC provided reinforcement will be 3 times pi by 4 multiplied by 16 square. that is 603 mm square. So note down this value. Later for deflection check, we have required all these ASC provided, ASC required, AST provided, AST required values, because based upon that we have to calculate few factors, and based upon that we can check the deflection of our beam. So this is the first major step, that is the design the beam section in bending. So this is our main reinforcement for our beam. Now let's calculate the stirrups, means what are the shear reinforcement required for our beam section. So for shear, first of all we have to check whether whatever the minimum reinforcement suggest IS 456, it is sufficient, or we have to provide some more reinforcement over it. So for that there is a few factors we have to calculate. Like first is the Doubly, that is the design shear. Its formula is VU upon B into D. Just put down the value. VU is a design shear that we already calculated in our first step, so you will get that value from there. B and D are the dimension of our beam, so design shear will be 1.54, design shear stress will be 1.546 Newton per mm square. Next we have to calculate tau c. For that we require the percentage of steel. So percent of steel will be equal to AST provided, that is our 6 numbers of bar of 20 mm dia, divided by B into D multiplied by 100. So we will get the percentage of reinforcement value as 1.49. So please remember, this percentage is for a tension reinforcement, not for the compression reinforcement. So based upon this value and one of the table given in the IS 456, we have to calculate the design shear strength of the concrete, that is the tau c value. So just what you have to do here, you have to find out where our percentage of reinforcement lies in between what two values. So for 1.49 we have to refer the 1.25 and 1.5 value, and for same both the value for M20 column we can take a 0.67 and 0.72. So our value lies between 0.67 to 0.72. So if you do the interpolation on your calculator, you will get the tau c value, and that is the 0.718 Newton per mm square. So this way we calculate the design shear strength of concrete. Another stage we have to calculate, that is the maximum design strength, maximum shear strength of the concrete. So for that also we have to refer one table given in IS 456. It will vary based upon the grade of your concrete. As we use the M20 grade concrete, so our maximum shear stress will be 2.8 Newton per mm square. Now we have to compare all these three stress values, and depending on that we have to conclude how our shear reinforcement coming out. So if you see in last video, we see in these three conditions, and we have to check in our case which condition is correct. So if you see here, first tau v and tau c value. So here tau v is greater than tau c, means it's like maybe in a second condition or maybe in a third condition. And if we compare the tau v and tau c max value, then it's seen tau c max is greater than the tau v, means the second condition is our case here again. So which means whatever the shear reinforcement suggests by the IS code, it is not sufficient for our beam section. We have to provide some extra shear reinforcement, and that we have to calculate using the standard procedure. So let's calculate those things. So first of all we have to find out how much shear resist by the concrete section. So whatever the concrete we put in a beam, how much shear that resists. So for that we have formula, that is tau c multiplied by b into d. Okay, design shear stress multiplied by dimensions of the beam. So just put down all the value. We can get shear resisted by concrete value is 90,827 Newton. Next, we have to calculate how much shear stress, for how much shear force we have to design the additional shear. So shear resisted by reinforcement, that will be equal to whatever the design shear force we calculated earlier. From that we have to deduct the shear resisted by the concrete. So that difference value we can get the shear resistance by the reinforcement. For that shear force we have to calculate the stirrups. So simply we have both the value, just put down. So we will get the VUS value as you seen on the screen, and for this shear force we have to calculate stirrup. So I select the 8 mm diameter stirrup, 2 leg 8 mm diameter stirrup, and for that formula is 0.87 times Fy into ASV multiplied by D divided by SV. So here ASV is the area of shear reinforcement that we have to calculate first. So we can use that value in this formula. So calculation is 2 times pi by 4 8 square. As we used the 2 leg stirrup, so we multiply the 2 factor to the area of 8 mm dia bar. So that will get 100.57 mm square. Just put down all the values, you will get the SV value. SV is the spacing of stirrups. So SV we will get 190.75 mm, which means we have to provide our 8 mm dia stirrup at 190 mm center to center spacing. This is the minimum spacing at that we have to provide. But for that we have to first cross check with our IS code provisions. So what our IS code suggests, the maximum spacing that we permitted is either 0.75 of D or 300 mm. So these both the values are higher than the required value, so which means we can provide the spacing as a 190 mm or lesser than this. So we select the spacing value 175 mm because it is more easy to provide at 175 mm spacing at the side. So hence here we conclude that we require 2 leg 8 mm dia stirrup at 175 mm center to center spacing from throughout the beam section. Okay, so this way we can design all the reinforcement for our doubly reinforced beam section. Now last step is to check whether whatever the dimension and all those things we providing here, that is sufficient for the diffraction criteria, or we have to revise this section or something like that. So let's check, because that is very much important, especially for the long span beam and the beam carry higher loads. So for deflection check we have to find out few factors. First is basic L by D ratio. So if you seen the last video, you can understand how this basic L by D ratio come. Still I can give a hint here. So this is a table for different types of beam. We refer the different basic L by D values. So for simply supported beam we can take 20 as our basic L by D ratio, and another factor that we require is Fs. So Fs we require to find out one factor which is called as a F1. So its formula is 0.58 times Fy multiplied by St required upon St provided. So this is our formula. Okay, so just put down all the values as we already calculate all the reinforcement area. So just put down, you will get the Fs value as a 226 Newton per mm square. And from IS 456, one of the chart that you can see here, using this chart we calculate the F1 factor. So if you have to find out the Fs chart here, 226, so 226 lie in between the 240 and 190, these two chart in between it comes, and we require the percentage of tension reinforcement. So percentage of tension reinforcement we already know, 1.49. so just you have to see properly where 1.49 touches the 226 value chart. So from that you will get the F1 value, that is the 0.98. Similarly, we have to find out another value, another factor, that is the F2 factor. As our beam is doubly reinforced section, means we have to provide the compression side steel also, so we require F2 factor also here. If you see in the singly reinforced beam design, there we can take as a just one value, because there no need to provide the compression reinforcement. So for that purpose we taken as a one value. But now here we have to calculate the F2 value. So for that also we have to refer one chart which is called the modification factor for compression reinforcement. So whatever the compression reinforcement we calculated, for that we have to calculate percentage of compression reinforcement. Like same way we calculate the PT value, we have to calculate PC value, and based upon that you have to see where our values lie on this chart. So you will get the F2 value, that is the 1.15. I am not going that much detail because it is very much similar to the PT value, so you can understand very much easily. Okay, so like that way we can calculate the F1 and F2 factors. And F3 factor, it is not required as our beam is rectangular beam, so just we taken as a one value. So from all these factors we calculate the maximum L by D for our beam section, that is basic L by D value 20 multiplied by F1, F2, F3. So just put down all the values, you will get the maximum L by D, that is 22.54. So this much ratio we can provide safely for our beam. Let's see how much we provided based upon our dimensions of the beam. So L by D that we provided, that is 6000, that is the effective span divided by effective depth 550. So that value coming out is 10.91. So which is very much lesser than the whatever the permitted, that is 22.54, which means our beam section is safe in a deflection. So we do not have to worry about the deflection criteria here. So which means our beam is safe in all the way, and whatever the reinforcement we provided, which is perfect for our doubly reinforced beam section. So this way we can give the detailing, like for our tension reinforcement, that is bottom reinforcement is a 6 numbers of 20 mm dia that we provide in a 2 layers. Top reinforcement we calculated 3 numbers of 16 mm dia. So this way we can provide a single layer, and the stirrup we can provide as a 8 mm dia 2 layer, 175 center to center spacing. Okay, so this is the detailing portion of our beam. Okay, so like this way we can design the doubly reinforced beam section, and that value we can use for our side and structure. So hope you guys understand the procedure of doubly reinforced beam section, and you people like this video, then please press the like button of this video. Also share with your friends and all the civil engineering students, so they can also get the benefit from this video. Okay, so thank you for watching our video. Thank you so much.